Alright guys, so in today's video, we're going to be talking about how to do a chi-square test for goodness of fit. By the way, we oftentimes abbreviate goodness of fit, GOF, so anytime you see that abbreviation, just know goodness of fit is what we're talking about. The conditions for doing a goodness of fit are very similar to conditions for other significance tests. Really, the one big difference is how we go about checking large counts. So let's run through them. First of all, data needs to come from a random experiment or simple random sample. 10% condition still required for standard deviation. We're taking 10 multiplied by our sample size, making sure that that's less than or equal to our population. And then large counts says that all expected counts must be at least 5, meaning greater than or equal to. Those words at least are important because in other chi-square tests, they need to be more than 5, whereas here for goodness of fit, they just need to be strictly greater than or equal to 5. So when we go to check those, remember chi-square test statistic is going to compare the observed and expected counts. So we've got to make sure we're using counts and not the expected proportions for each category. And then when we're checking that large counts condition, we're looking at the expected counts, not the observed counts. It's actually okay for the observed counts to be less than 5 as long as the expected values are at least 5. So for our example that we're going to look at, it says according to the 2000 census of all U.S. residents aged 20 and older, 19.1% are in their 20s, 21.5% in their 30s, 21.1% in their 40s, 15.5% in their 50s, and 22.8% are 60 and older. We've got our table below, which shows our age distribution for a sample of U.S. residents aged 20 and older. So you can see the counts for each of those observed values for those in their 20s, 30s, 40s, 50s, and 60 and more. Members of that sample were chosen randomly by dialing landline telephone numbers. Does this data provide convincing evidence that the age distribution of people who answer landline phones is not the same as the age distribution of U.S. residents? So let's start with our statement. In our statement, we're going to say what exactly our hypotheses are. So in our null hypothesis, we're going to say that the distribution of those who answer their landlines is the same as the distribution according to the U.S. Census. And then our alternative is simply going to be the distributions are different. And like in previous significance tests, we're going to include our significance level. Let's go ahead and test at 5%. Okay, so there's our statement. Next, let's run through our plans. We're going to say what exactly the test is we're doing. This is going to be a chi-squared goodness of fit test. So chi-squared and then GOF, I'll go ahead and abbreviate, goodness of fit test. Next, let's check our conditions that must be met. The first is randomness, which it does say up here that we are randomly dialing landline telephones. So yes, that condition is met. Next, let's check 10% condition. There were a total, it says, of 1,048 people who were dialed. Is it reasonable to assume that there are more than 10,480 that they could have had in the population? And I would say definitely that is a reasonable assumption. Next, we need to check, are all of our expected counts greater than or equal to 5? And so to do that, we need to find our expected counts. So let's go ahead and below the counts for each category, let's go ahead and find our expected counts for each of the categories as well. We'll do that by taking the total multiplied by each of the probabilities. So starting with 1,048, we'll take that and multiply by 0.191, which was 19.1% in their 20s, which is 200.168. Next, we'll do the same 1,048 multiplied by the 0.215 for their 30s, which is 225.32, and so on. If you want to fast forward the video so you can see those final numbers, feel free. I'll go ahead and continue to type them in. Next is 0.211, which is 221.128. Next, we'll multiply by 0.155, which is 162.44. And last, we'll multiply by 0.228, which is 238.944, which pretty clearly all of those are greater than or equal to 5. So it looks like all of our conditions are met. So in step 3, let's go ahead and do our calculations. We're going to be looking for a few things here. First would be our chi-squared test statistic. The next would be our p-value. And then last would be our degrees of freedom. So let's go ahead and find each of those. Probably going to be easiest to just let the calculator do the work for us. So let me show you how to do that. First thing we're going to do is enter all of our data into list 1 and list 2 of our calculator. So list 1 is going to be our observed counts. List 2 is going to be our expected counts. So 141, 186, 224, 211, and 286 for the last. This is where actually in the future, if you want to save yourself a little bit of time, since you're going to need those expected counts anyways, it's sometimes easiest to just do that in list 2 because we're essentially going to be typing in exactly what we were doing in the first place, taking 1048 multiplied by 0.191 for that first value. And then that way you can just check them from your list 2 rather than having to type them in twice. In the future, just to save yourself a little bit of time, you might consider doing that next time. All right, so now I've got list 1 as all of my expected, or my observed counts. I've got list 2 as all my expected. I'm gonna go back into stat. I'm gonna go over to tests, and then I'm gonna be choosing the chi-squared goodness of fit test, which for me is gonna be option D. Make sure you do the one that says GOF or goodness of fit. We've not talked about that chi-squared test, which is option C. We'll eventually get to that in later sections. So here's where just make sure that they are in the correct spots. So observed, we have in list 1, expected in list 2. If for some reason yours are different, make sure and change those here. And then for degrees of freedom, remember that's the number of categories minus 1. There were 5 categories in this case. Minus 1 tells us that there are 4 for our degrees of freedom. And then we'll go ahead and hit calculate. And so here are going to be our values. For chi-squared, I'm going to round to 2 decimal places, 48.17. And the p-value, I'll also do the same, 8.7 times 10 to the negative 10th. So a very, very small p-value. Keep in mind that would be 0 point and then 9 zeros before you get to the 8 and 7. So a number which is very, very small. Okay. So let's now write our conclusion based on that. So we're going to say because the p-value of 8.7 times 10 to the negative 10th is less than our significance level of 0.05, we are going to reject our null hypothesis. In other words, there is convincing evidence of a difference in the distributions of the U.S. Census and those from the landline phone distribution. Okay. So then that leads us to a question now, which is when do you do what's called a follow-up analysis? And then how do you actually go about doing that follow-up analysis? Well, the first question, when should you do a follow-up analysis? That should be any time you reject the null hypothesis. So then how do you go about doing a follow-up analysis? You're going to use the contributions list, which is actually what that list is in our calculator. So use the contributions list. And that's the one again from our graphing calculator. So if you look below degrees of freedom, you'll see CNTRB, which stands for contributions. So what we're going to do is use the arrow keys to scroll through and figure out where was the largest contribution from. Keep in mind, all of these contributions are essentially how much each of the categories contributed to that chi-squared value. Obviously, the bigger the contribution to that chi-squared value, the bigger the difference between our observed distribution and the one that we were investigating based on our claim. So for our follow-up analysis for the problem up above, and this would typically go along with your conclusion, so we're doing it separately here, but just for future chi-squared tests, anytime we do this, make sure to include that as part of your conclusion step. Let's figure out which one contributed the most. So our first contribution was 17.4. That would correspond to the first category. The first category was those in their 20s. The next contribution, and again, you can use your left and right arrows to scroll, is 6.8 from the 30s. The next contribution is 0.037. That was from the 40s. Next is 14.51 from the 50s. And the last is 9.27 from the 60s. So thinking about those values, that first value actually of 17.49 was from those in their 20s. That would then be the age group that contributed the most. So what we'd say for our follow-up analysis is that the 20s age group contributed the most in the decision to reject our null hypothesis. All right, guys, so from this point on, it's not going to be something that we're reminded of. We're going to have to remember to do that follow-up analysis anytime we reject our null hypothesis. Guys, that is it for today's video. Until next time, have a good day.